Here's a criterion for when two left ideals generated by two primitive idempotents E1 and E2 carry equivalent irreps. Namely, if this product here E1 Q E2 is non-zero for at least one Q in the group algebra. Okay, let's call the left ideals Lj. So we get them by taking the group algebra and multiplying with Ej on the right. Let's look at this direction here first. So we have this E1 Q E2 expression which is non-zero, and let's give it a name. Let's call it S. So there's some non-zero S in the group algebra. And now we define a linear map capital S from the group algebra to the group algebra. And we define this by right multiplication with little s. So capital S acting on R is R times little s. Now let's see what happens when we apply capital S to E1. Then we get E1, E1, Q, E2, because that's just little s. So we can absorb the E1 here, and we get back the little s. So we see that this is not 0 when we restrict it to L1. So S restricted to L1 is not the 0 map. And actually, when we look at this S restricted to L1, then it's just a map from L1 to L2, because we have this E2 here at the very right of our product. So the result is in L2. Okay, now we can play with this and say, what's SRP? Well, that's RP little s, and that's the same as RSP. So we have something commuting here. Here, this commute. And that's true for all R and P in the group algebra. But maybe we don't need it for all R and P in the group algebra. Let's specialize this a bit. Let's say we use this for R in the group and for P in L1. Because then what we have here are the representations of this group element R on L1 and L2. So this equation here now reads S gamma 1 of R is the same as gamma 2 of R S. And Schur's lemma now tells us that since we have a non-zero S here, checked this earlier, that with this S the two gammas are equivalent. So gamma 1 and gamma 2 are equivalent. So that's enough for this direction. Now what about the other direction? We start with equivalent irreps. So this means there is a linear map from L1 to L2 such that, say, for all R in the group, we have that gamma 2 of R is the same as S gamma 1 of R S inverse. Or if we want to rewrite this that's just S gamma 1 of R is equal to gamma 2 of R S. Okay, but let's spell this out on the group algebra as this. SRP is the same as RSP, let's say for all R in the group. That's what we had here. And for all P in L1. So then we have the representations on L1 and L2 here again. This one is an L1 and this one is an L1. So the S acts on L1. But actually we can extend this S by linearity. This holds, say by linearity, this holds for all R in the group algebra. If this is true for all R in the group, then by linearity we can go to the group algebra. Now we can do this here. Let's look at capital S times E1. That's definitely in L2, because S maps L1 to L2. And let's give this a name. Let's call it little s. Now we know that this little s is equal to little s times E2, because multiplication on the right with E2 does nothing to something that's in E2. Okay. So what do we have here? Now what is S times E1? Oh, now let's look at S times E1 E1. What's that? We have this commutation property here. So we can write this as E1 S E1. Just commute it here. And now the S times E1 is the little s, so we have E1 little s. But little s is the same as S times E2. So we have this combination E1S E2. But on the other hand, we know that E1 times E1 is E1. So here we have S applied to E1. That's just little s. And that was non-zero. So we're done. We have that this product here is non-zero. That's exactly, see, it's still up here, what we need for the other direction.